So the join me today is basically on Performance Copilot. I'm going to start introducing some of the statistics, but really this is just an introduction, so to speak, to the metrics themselves and how to interpret them. So Performance Copilot's been around since the 90s from SGI. It was originally a licensed product, and somewhere around 2000 or something, they open sourced it and dropped the licensing when they moved into Linux. Eventually, the developers for Performance Copilot left and started their own little group, and they still maintain it. Ken McDonald, Nathan, people like that. You will find it everywhere nowadays in the distributions and also like in the cloud, AWS and stuff like that. They have containers for it. In the long run, I don't really care what tool people use, but I'm spoiled by Performance Copilot.
Right.
But bottom line, it's interpretation of the data, but PCP is giving me a lot of things that I don't have in any free type of tool out there. And I haven't played with the advanced Hewlett-Packard control consoles or anything like that. But anyway, for free software, this is the best. Before this was basically the sysstat package and the SAR command. And back in the 80s, 90s, I basically had scripts that would run SAR ASCII output into an awk script and plot it with GNU plot, or something from MIT called XGraph.
Right.
I don't need the tool anymore now that there's a web interface and all that sort of thing here. Now, there is in our approach for analysis, just to review that, the first thing was to get an inventory of the system. And we're going to go through this over and over again, but that's not today's topic. After we know what we got for hardware and software, then we got to figure out what metrics we care about, establish our metrics, and make sure we're collecting them. So, for example, NASA Ames, we would want comprehensive system accounting on, various other metrics that a site may want to collect, including things like mean time between interrupts, downtime, all kinds of different things the site's going to collect. So in that step of establishing metrics, you're also looking at your benchmarks, because that's where you get your quality of service metrics. In other words, how well the application performs on the system. Now, after establishing metrics, then you've got your instrumentation, and that's what we're moving into. Okay?
All right.
After instrumentation, you then get into a chicken and egg story. If I'm just starting a benchmark, I don't have a baseline to get to yet. So I got to start running my workload, looking at it live, and then get a baseline. But if the system's already in production, I got to get my baseline first before I start drilling down into the live data that we're going to do today. It's all relative. I don't want to be drilling down in 1 second samples without seeing the big picture.
Right.
Okay? So when I'm looking at a metric like how many times a process swaps off the CPU called context switching, I'd like to know what it was like over the last month. I need some reference. Okay? And I have to point out again, in my analysis, the first level is the Performance Copilot or SAR data, and we're basically looking for behaviors. This is telling us what to look for. It's a behavioral tool. To me, Performance Copilot is kind of an oxymoron. It's not a performance pilot. There's no performance data within it.
Yep.
To me, performance data is time to solution, time domain. Everything in PCP except for disk activity is in the frequency domain or percent utilization type counters. So I could have a CPU that's 100% busy and getting no work done. Okay? So SAR and PCP are telling me what to look for. Then I have to go to my second level of statistics, and that's the quality of service metrics, and that's the time domain.
Right.
So we're really looking at time domain in our studies right now. When you're looking at your FIO tests and stuff, we're looking at bandwidth and latency. I guess latency is a quality of service metric, but in general, we're looking for behaviors as you run your FIO tests.
Right.
So the objective was when you're running your tests, you'd be able to poke in and see what's happening. Be able to get some bandwidth tests and things like that going. So, health of the system, I'm a shrink looking for behavioral problems. The second level, quality of service, I'm in the time domain looking for time to solution and whether I care about something. So SAR may see CPU utilization 100%, but my work's taken a week when I know it's a half-hour work. So the time domain tells me whether I care and what I care about. Right now, for example, the MEM SQL that we have going, we have I/O going on in the background for basically keeping a checkpoint copy of the in-memory database off in a persist directory. And that I/O is in the background and not part of the direct queries, but when we start ingesting or changing the contents of the in-memory database, the persist directory has to be coherent to that. So that I/O might be of interest to us, but it may not be part of the time to solution. Okay? So again, PCP is telling you what to look for. It's the time to solution, the quality of service metrics that tell you what you care about. The third level then was the profiling. So now at the profiling level, I'm looking at names of programs, names of users, names of subroutines. Oftentimes profiling is basically looking at the program counter and figuring out where the program counter is all the time. We can profile I/O, we can profile system calls. When I'm profiling, I'm an efficiency expert.
Right.
I'm trying to look for non-optimal resource consumption. So SAR might tell me my CPUs were 100% busy. Time domain says I'm spending longer than I want. It's not an acceptable time to solution. And then when I'm profiling, I'm looking for different types of non-productive resource consumption, like inter-process communication. What I've talked about is a stuck barrier. Multiple threads trying to talk to each other and playing phone tag with each other. So the profiling stage tells me about these non-productive behaviors. Right now on Marvin, we have a 6 terabyte MEM SQL database. The bottleneck right now are the page tables.
Right.
And we have like 16 MEM SQLs, and each of them have almost like 700 for 16 of them. But then there's 473 threads for each of these 16. And that's making huge page tables. And in fact, 2 commands, lsof and perf. And I don't know why, but they open up every process's page table. And I can have ls 2 hours later still going through the page tables on Marvin and never getting anything done.
Right.
So that would be an example where Marvin might look healthy from PCP data, but the time domain says this is taking forever. And then when you're getting into profiling, you're finding out the more details and identifying the behavioral problem. So it's profiling that tells me the difference between this is a stuck barrier, this is page misses, page faults, this is different types of problems. The profiling tells me that. So for profiling, I need names of programs, I need subroutine names. I would even like to get down to a line number.
So
the fourth level, I'm sorry?
Question for, can PCP really get to that level, or would you need to switch to a tool like GDB?
Yeah, PCP won't get you line numbers, no.
Okay.
Even perf won't get to that. GDB can, but other profiling tools like Intel and perf suite and stuff like that can get down to a line number.
Okay.
So we'll get into that into summer at this rate or something. But when we actually start the CPU application tuning module, we'll get into that in more detail. So when I attach, I can't even run perf to look at it, but then when I S-traced, I could see that it was spending all this time just going through every process's map file, every process of page table. Kind of off topic of PCP, but a page table is the mapping of the virtual address that the program knows to the physical location in memory. So whenever a program has to go get an instruction or read or write to a virtual memory address within the program space, it has to find the physical location of that page.
Right.
That is first looked at on the processor in something called the translation Lookaside buffer, the TLB. This is basically a very, very small cache of the page table. So when my program can't find the physical address in the TLB, then it takes a page fault to the kernel, and then the kernel has to go to the page table, find that page, get the physical address, and put it back into the TLB. And right now, Marvin has got two big page tables, and you can spend a lot of time managing and finding pages in those huge page tables. We would like to look at huge pages to reduce the page faults, so to speak. But anyways, I'm off topic, but I was trying to give an example of where PCP is telling me what to look for. The time domain from something tells me whether I care about it or not. The profiling isolates the type of behavior that I have. And there is a fourth level that is actually getting into the hardware counters themselves. So profiling, you're getting subroutines and stuff like that, but now at the hardware counter level, you're getting how many cache misses did I do, how many floating point operations did I do. The processors nowadays, not all of them, but the high-end processors keep track of how many times an instruction happened. So you keep track of how many branches and stuff like that. And perf can get to that, and there's PAPI and stuff like that. So 4 levels. So Performance Copilot just tells me what to look for. We are not pursuing the other 3 as we drill down into data with today's topic. Okay? So Performance Copilot, let's just see what we got here. We're on NFS server. What's our operating system?
Let's see. Let's do our
cat.
Well,
I'm doing a quick inventory here.
hey, no, I was trying to. We don't have the inventory scripts on here, do we?
No. They're probably their SOS report might be, or this is slash, so it'd be SUSE config. Anyway, I just want to do quickly because you don't always have inventory tools. So cat, ITSI, asterisk, release, asterisk.
Oop.
Yeah, too much. No, an asterisk in front and behind release. There you go. Okay?
All right.
That's an important one. Remember that all the time. You got to start with that. So we see we're running /12 SP2. Okay, let's do an LS CPU.
Hold on, I'm just writing it down. Cat. Let's see.
Just LS CPU as a command. One word. Okay? So there we see we've got 40 CPUs on 2 NUMA nodes, 2 sockets. I do see that hyperthreads are on. Notice the node 0 CPU, 0 to 9, and then jumps to 20 to 29.
Yep.
That's a good indication of hyperthreads being on.
Right.
So the physical cores are 0 to 19, and then the virtual cores are 20 to 39.
What's the deal with the genuine Intel ID?
I don't know.
Oh, okay. Never mind.
I'd have to look into it. It's something that's coming off the processor and the firmware and stuff. I don't really care. There's a ton of stuff there. I don't care about that. It's a good question. I just don't care. But I can see that it's E5 2640 running at 2.4 gigahertz.
Yeah.
That can be looked up. There's something called BOGO MIPS. Do you see that, BOGO MIPS?
Yeah.
That's just a timing loop. When the kernel boots up on the first time, it does a quick estimate of how fast the CPUs are. It needs that for timing loops and stuff. So it's just a rough thing for the kernel to make a quick judgment of how quick the CPU is. Okay? I see I got 32K of L1, D for data, I for instruction, 256K for L2, and those are unique to each core. And again, I've got 10 cores, 0 through 9 on each socket.
Right.
And then 10 virtual cores. And then the L3 is also referred to as the last level cache, and that's at a 2.5 or 25 meg, I'm sorry. Right? 25 meg for the L3. That's shared between all 10 cores.
Okay.
And that's also referred to as the last level cache or uncore, because it's not part of the core, the L3 or LL last level cache, LLC. Okay? Any questions quickly? So we know we're running SLES 12 SP2. We're on a 40 CPU system. How much memory do we have?
Let's do meminfo.
Yep. More. More /proc/meminfo.
Okay. And
so it looks like a 256 gig.
Yep.
263 in powers of 2. So we got 253 gig of memory. That's on 2 sockets. So it's about 128 gig in each socket. Do a DMI decode and pipe it into more. DMI decode and pipe it into more. And keep going down. We want to find a DDR. We want to find memory. Try /uppercase DDR. And there are options on DMI decode to print out just one thing. But okay, so I see a DIM here. I see its location in the chassis. I'm not really seeing anything that tells me how big it is or anything. Keep on going down. There's something there. What's that? I got a clock feed there. I got a part number, serial number. Micron is the manufacturer. Oh, there we are. 32 gig in size.
Yeah.
Okay. So we're running through an inventory real quick. So these are 32 gig DIMMs. They're running at 2.5 gig. They are a DDR4.
Yep.
Any questions?
Nothing so far. This all makes perfect sense.
So let's quit out of there. So we've looked at CPU, we've looked at memory. Let's look at disk with an LS-SCSI.
Yep.
And I'm skipping over PCI. LS-PCI is too noisy. I'm not really interested in LS-PCI because you'll get a ton of stuff. Okay. So this is NFS server, and remember last time we created and unintentionally created SDA to SDJ. I wanted one that was 10 wide, but I got 10 that were 10 wide.
Yeah.
Remember?
I remember.
So again, that's all playing around and practice and stuff like that. So we're going to play with those, and when you get time in the next week from what your schedule sounds like, we'll get back to the FIO experiment. Do an LS on /LS-1 on / LS space dash backup -1 on /.
Up.
Okay, so I thought I built them on here, but I guess I took them off. So do more on fio.daw.ssh. Oops, .daw, fio.daw. No, one word. fio.daw, tab it, there you go. So my script was basically looking for file systems that are created there. Notice I'm starting with /single. So that would be just a single drive.
Right.
And then 40 would be just 4 that are striped. And then 4-1 would be 4 wide that are mirrored. In other words, 8 drives in it. And the 4-5 would be 4 drives plus a parity, so 5 drives in that. Remember, the prior one was 8 drives because it was a mirror. And then 4 + 6 would be 6 drives. You get my point? And then you see there are 4 topology in, and I was tweaking that thing to go through the different file systems that I create, because there's not enough disk drives to create all the different flavors or variations. Okay? So basically, it's going to go through that loop, and you would edit. You see that for loop, you would edit that to be the order that you want. And 256 indicated these were a 256K by request. And I'm not sure what the default was. I think it was 256.
Mm-hmm.
Again, we were going to do two ends of this, 256 and 64. So
Right.
I'm hoping to see bandwidth be good at 256, but I'm hoping IOPS to be better at 64.
Okay.
And again, this goes back to Ferrari School Bus 747, and the whole purpose of this FIO test and this heat map was to understand how different workloads run better on different file system designs, right?
Yep.
So anyway, let's break out of there. So we're going to, later in the week, create a bunch of those, but do a grep on that thing. Grep FIO, and then, no, just for the FIO command in that script. FIO space, FIO.daw.sh. So there's the FIO command.
All right.
So it's going to, you can look at the script, but it's going to circle through each one of these FIOs for each request size.
Mm-hmm.
And then we're doing random reads, random writes, and within each of them, I'm doing a single job, multiple files, multiple IOPS. So
Yep.
we're kind of going single-threaded and then asynchronous multi-threaded, lots of IO threads. Does that all make sense?
Yeah.
So anyways, I'm kind of done with the inventory, but that's where we're going to go, is to be able to build those file systems and modify that for loop and be able to run the FIO test in all these different flavors and get a table that we can heat map to. So, putting that aside, back to Performance Copilot, because I want you to be able to observe these FIOs when they're running.
Yep.
And by the way, notice in all of them, there is a $ direct.
Yeah, I see it.
So all these FIOs are doing direct I/O. They are not going through page cache. Otherwise, you would not get disk speed. You would be getting memory speeds and cache influences, and might be real good for a while and then drop down to disk speed, things like that.
That makes
it's
sense.
all being done with direct I/O. We're going straight to the disk. Now remember, there are three types of I/O. Cached I/O is what VI is using. I'm annoyed with all these database engines like MemSQL that's doing cached I/O to read in our case, 6 terabytes got to come in from disk, and
Yep.
all that, and lots of little cached I/O. And so if I've got a 6 terabyte machine, and I got to read 6 terabyte into memory, and then my application's going to be 6 terabyte, you got a problem, right?
Yeah.
Now you got a page cache that wants to be 6 terabyte, and you got an application that wants to be 6 terabyte. They're going to fight each other.
Mm-hmm.
So people don't seem to understand when direct is good. Moving on. Let's do it clear.
Yeah.
So the point was to get PCP running. Just do a RPM-QA and grep for PCP. So it is not installed right now. That's LDAP.
Yeah.
Okay? Now let's do a zipper PA and grep for PCP. Hopefully our repositories are somewhat active. Since I swapped, we may have a problem here. Break out of that. Oh, there we are. I got to be careful because we swapped 15 to 57, so our repositories are not on 15 yet.
Right.
I do see PCP is in there in the /12SP2 pool, but I don't care about that one.
Yep.
I'm going to install the one we built. So let's go to YAP. I was just pointing out that it is in Slats, it is in Red Hat.
Uh-huh.
Go to software repositories, so tab to the right and down to the end. Oop, up. Yep, down to the end. And we are going to add a repository, tab down to add. Remember, most of those repositories are for updates. Keep tabbing. Tab down into the, I think you're down arrowing, aren't you? There.
Hold on.
Were you down? Was that a down arrow before?
Yeah, it was my mistake.
Okay. Yep, tab one more. I guess one more. There we are, add. You with me?
Yep.
So we want to add in an NFS. And again, you see that download repository descriptions. If it's not a repo, you can, if it's just RPM without create repo, 15, then you could deselect that one. So we're on 15.
15, yeah.
And then dash install, and hang on while I get, I'm logging into FCL server to get the actual path.
Yep.
I'm installing the ones we built.
Yeah.
So it's /12 underscore DAW slash.
That's
That's
12.
12 underscore DAW underscore.
DAW.
DAW. Yep. And then tab to next. Okay, and then tab to OK. Yeah, you just hit enter. And now go up to software management, up arrow.
Mm-hmm.
And type in PCP. So there's a whole bunch of things in there. Let's tap back to the filter
Okay.
and down arrow and pick the repository one up there. And then down to my repository /12 underscore DAW. Tap, no, you were there, hit enter. Tap there, down arrow. Oh, no, back up, tab back. Down arrow to the last one. That's good, there you are. That looks like it. So these are the ones that I built, and they're not perfectly clean. I still have like startup scripts or init.d type of problems. But go up one and select PCP. And hit enter. There you go. And let's go down and see what else we want here. I don't care about any of the imports. Keep going, keep going. There's something there. See all these PMDAs? That's a performance metric domain agent. That's a way of adding statistics that are outside. So, you know, there's luster, things like that. Why don't you go up? There was a DM one. Go up. I was just curious. Go up. There was a DM, which looks like device mapper. That might be relevant to us right now, so let's select that.
Okay.
And then go down. You got temperature sensors, you got mail, you know, NFS, GPUs for Oracle. SGI doesn't have all of these. They have a subset, which is why I went to the generic source. And that all looks good. Keep going down. And that looks like it.
Yep.
I was looking for a PCP-GUI. Is there a PCP-GUI up there?
Let me check. It doesn't look like it.
Huh. Okay. So anyways, let's tab to accept.
All right.
Go ahead. And finish.
Yep.
Again, I was just going to the latest one. Go back to that software management, though. Go into it and do a search for PCP-GUI. Go ahead. Anything?
Doesn't look like it.
Yep, okay. Let's just get out of there then. So that's I know it's in the SGI distribution. I'm not sure why it's not in the distribution we built, but go ahead and quit out of there.
Yep.
Okay, so PS-E and grep PMCD. PMCD is your data collector. If that's not running, PCP has nothing to talk to.
Mm-hmm.
That has to be running. Now, we installed it, I believe, so do an RPM QA and grep PCP. PCP.
Oh, ooh.
So it did get installed, just double checking. Now do an RPM QL on PCP, pipe grep. No, I want a grep for system. Oh, we need the name PCP, we need the name of the RPM. PCP, pipe grep, system. So I'm looking for the startup scripts.
Mm-hmm.
Okay. So you see what I'm doing? I'm using QL to find the rest of the pieces. Right?
Mm-hmm. Yep.
So I find the package with QA, I find the files that are in the package. So in this case, let's do a system CTL, enable pmcd.service. Oh, what happened?
Oh, forgot an S. Hold on.
Yeah,
Okay.
there we go. Notice that it did a link.
Yep.
So that RPMQL was in user lib, and now it's linked it into the ITSI systemd directory, which is what is actively used during startup. Okay?
All right.
Now it hasn't actually started yet, so let's do the systemctl start, pmcd.service. Oh, no. PM systemctl start. You got everything wrong. Systemctl start,
Uh-huh.
pmcd.service.
Okay.
Now it's ps-e and grep pmcd.
Okay.
So we do have it running now. Try with an EF.
Mm-hmm.
Do the PS with an F. Let's see if there are any arguments on it. No arguments to it.
Oh.
Okay. Now, go into var lib PCP. Do an LS. And we're only right now interested in, config, CD into config. And I'm going to talk about PM chart later, but the one we care about is PM logger, CD into PM logger. Do an LS. Okay, not much there. A little surprised. I was expecting to have a little bit more there than that. Well, let's just find out here. SFTP to FCL-server, the FCL.server. Go ahead. And then go into var lib PCP config, PM logger, and copy that config.default. No, mget, sorry. Mget. And quit out of there. Do a more on the file. So this is the list. We're saying every 300 seconds I'm going to get a snapshot. Okay?
Yep.
So PM logger is going to be a daemon up and running. If either of these daemons cracks, there's a cron event typically to restart them, but I don't think we have that cron event in place yet.
Mm-hmm.
So those are all the statistics. Quit out of there. Do a PM info-T, pipe into more. T, table, T as in total, type, yeah, there you go. So, as you add those performance metric domain agents, PMDAs, additional metrics are made available.
Yep.
I'm kind of interested in like that JVD2 statistics for what's probably extent 3 or something for the journal. You got HI&D for hardware, keep on going down. There's always new metrics being added, and then there's the actual kernel statistics, and we're going to be digging through all these ad nauseum. Go ahead and quit out of there. Okay, so let's do your system CTL. Enable pmlogger.service. And then let's start it. Now the config file I gave you was meant for SCL server, so there will be some differences in metrics, for example, different file systems and stuff. Right? So I don't really care about that right now. But let's go into var log PCP. Do an ls. Let's cd into pmcd. And let's do a more on pmcd.log. So not a whole lot there, no errors or warnings or anything like that there. There is a problem that I've been around this with PCP developers before, but there are 2 ways of running a performance metric domain agent. One is as a child and one is as a separate shell.
Yep.
And when it's a separate shell, you get timeouts and you get zombies.
Oh, yeah.
A zombie is a process that is dead, but its process table entry cannot be released.
Because the parent
gone.
process is dead, yeah. So you have to reap the dead children.
Somebody's got to take the funeral.
That joke was that was the joke from our systems class at UMD. Was our professor liked that one a lot.
Yeah, and this is when the political left would say fuck, cry foul, and want to change terminology so that you don't have folks turning into zombies. But let's move on. Okay, now let's go up a directory.
Yep.
And into pmlogger. I do expect to see some errors there. So let's look at that log. I didn't complain about anything, so I'm okay. Let's go into NFS-server. So there are our files. Let's do an ls-l.
Yep.
Not too big yet, but every 5 minutes to get a sample. Let's look at that log.
Latest?
No. You can look at latest. Go ahead and look at latest.
Nothing much.
That's just to keep track. This is portfolio, PM, AFM, portfolio manager thing. So that's just to keep track of the current. But we wanted PM logger. No, those are binary. You won't be able to look at those. PMlogger.log. And page on down. Let's get to the end, looking for errors. Now, I've been tweaking this in the past month. Keep on going. We can get to the end. I'm getting bored. And could probably still be cleaned up and stuff like that. But okay. So I didn't see any errors in there either.
Okay. So here's
Now,
a question for you about
Okay.
PCP then. So if we're doing 5-minute snapshots, and if we want to do this over a really long time domain, let's say maybe I want to measure the performance that we're seeing in the data center for a given month,
Yep.
isn't there the risk that the reports are gonna start filling up the disk or becoming a
It
storage
depends
issue?
upon how much. It depends upon how much you collect. Depends upon how big your disk farm is, how many paths to the disk farm. That's going to be the biggest disk consumption. Okay.
Right.
So it depends upon what you're collecting, and disk farms being the biggest thing that has lots of entries and stuff. Let's go to Marvin 1. Let's SSH to Marvin 1. Everything's SGI.
Uh-huh.
Seed into var log PCP PM logger. Let's do an LS. Let's do an LS on Marvin. Notice it's got the full path name, actually. I don't know about the slash. No slash. There you go. So what do we got there? 516, 525. So it looks like we've gone from the 16th right now. And they are compressed.
Mm-hmm.
Let's do a DU-H. DU-H on that H, human. So there's only 3 gig in there right now. Let's do an LS-L. On that subdirectory, ls-l on Marvin 1 tab. Okay, let's do it with an H too, ls-lh, make it friendly. And what do we got there? I'm not even seeing many that are in the gig. But again, it's a small disk farm.
Yep.
Okay, now it can be possible that that does become a disk consumer and stuff. When the DMF package is loaded, it actually is running PCP in a different directory under barlib PCP storage, and then barlib ends up filling up. So it is of concern.
Yep.
Okay, so let's get out of there.
Yep.
There is the ability to get to this thing live now. Let's put pminfo-t on kernel.all. pminfo, yep. Actually, we don't even need the T. Just do a pminfo kernel.all. Okay, so now do a pmval, pmval. Yep, space. And then we want the metric name, but you kind of it's scrolled off now. Kernel.all.load.
Okay.
Let's try that one. And now we're able to actually get to the data live.
Okay.
Now I'll come back to a flow chart of all these tools. And we don't have a whole lot going on right now. Hang on here. Okay, so anyway, break out of there. The next thing now, so we can only actually, I didn't have any data to look at there, but we do have a PMCD that's up and running and talking. I forget what port it's on. It's like 23 something. Anyway, I'd have to look up the man page to find the port that PMCD is listening on.
Mm-hmm.
But now let's go to your workstation. Looks like you're running Windows.
Yep,
You ever used, what is it, Katina on the left? I never used the sucker. Anyway.
This is Windows 10.
I know. But that assistant that, anyway.
Oh, Cortana.
Bring up a browser now. So I want to run distributed here. I didn't want to run PM chart through VNC. I want to run PM chart on your workstation.
Okay.
So PCP.io, no, PCP.io.
Hold on. It's.
Sure.
I already. I did install
That's fine.
PCP yesterday.
For demos of the recording, if Brian or others want to see it, is why I'm doing this.
Okay.
So over on the right, click on download. And then you got your various distributions. So you can see that it's in Debian and Ubuntu and stuff like that by default. There's the Windows one. So there you are, down, here, there, right there. And again, they warn that they're pretty outdated, but it's what I'm using. Question?
Yeah. No, the only thing I'll mention is I did all this yesterday as well.
Yeah. Again, I'm doing it for anybody else that uses this recording.
Okay.
So let's click on PCP. I'm trying to get Brian up to speed on it. Let's find the bin crate. And version 9.11 over on the right, is that?
Yep.
It was a little hokey finding these things. Let's click on Set Me Up. That's how to download it that way. I don't really want to download it that way. Quit out of there. I'm not used to this. When you click on the pilot thing on the left, right there, up, that thing, up, down, does that give us the links?
Nothing.
Files. There we are, files. Okay.
Yep.
Got lost there. Now you said you already installed it?
Yeah.
So anyways, you can blow that off. Again, I was just trying to get this started. I think anybody on Windows knows how to just open an MSI file and go through it.
Yep.
Okay. Any questions?
Nothing so far.
So now let's open up PCP on your laptop. There should be a little glider thing, icon somewhere. There you go. I don't want the shell prompt.
Oops. Hold on. Let me deal with Cortana here.
PCP includes some Xming and some Linux tools for Windows. Okay, that's looking real good. That's what we want.
Yep.
Any questions right now?
Nothing so far.
Now, when I have an archive, there's a -A option on PM Chart that will allow me to open up an archive, but we'll come back to that some other day. So, go to File and click on it to get a pull-down menu, and we're going to open View. Now, see the PC in the lower right box, just above Cancel. Lower right, above Cancel, one above it. There. Click there and put in 10.1.10.53. Without that, it's going to go to your PC, and if PMC is not running on your PC, which it could, but we haven't turned it on, so it would blow up without that. Okay? Now click on CPU.
Yep. Right.
And select Open. Okay?
Yep.
So these are our first sets of metrics. Time spent running your program in the program itself, including libraries and such. The red is time in the kernel, in the operating system, doing system calls, and in particular, spin locks within the kernel.
Yep.
Both of these we profile with perf, for example.
What?
There's also things that might run under NICE, disk defraggers and cron events that might run at 4 in the morning. The find command for the locate utility, they might be running under a NICE when they start up. But that's basically user time for commands that have a different NICE than the standard. And you don't see it too often, but usually you look for a cron event. The next one is my interrupt handler time. Okay, you usually don't see that, but you can. And when you have a high interrupt handler time, it might be packet switching from databases or something.
Mm-hmm.
Then we have wait time. That is I/O wait, waiting for I/O. And that's what you're going to be seeing when you're running your FIO test.
Mm-hmm.
So this is 100% utilization. I've got, 40 CPUs. If all 40 CPUs are 100% busy, the chart will all be filled and there won't be any green.
Yep.
Okay? Now, steel is for VMs, KVM and stuff. So I'm going to mess with you here a little bit. Go under Edit.
All right.
Edit Chart. Go to Edit there, Edit Chart. Oops. Edit Chart. And see the steel? Get your cursor down where the steel is.
Yep.
There you are. Select that. And we should be click on metrics, and there's an X on metrics, and get rid of it. Go ahead. And it's gone. Click OK.
Mm-hmm. Yep.
You okay?
So far, so good.
Okay, we're building something here, so let's go under File, Open View. And this time, let's select the load average. And let's do another one, Open View, and let's do memory.
Mm-hmm.
And let's do one more for disk. Now, I'm not expecting to know all these metrics all at once, but the load level, that load average, so it's a rolling or smoothed average of all the processes that are running, runnable, or non-interruptible. Basically, go to the window behind you on NFS Server.
Mm-hmm.
Bring up top.
Yep.
And notice the state. 1, 2, 3, 4, 5, 6, 7. What's the ninth column there? The S.
Uh-huh.
Between share and percent CPU. So S says it's sleeping. R says it's running. But a D says it's non-interruptible.
Mm-hmm.
And non-interruptible are part of the load level.
All right.
Okay? So anyways, we'll come back to that. Let's go back to PCP again.
Yep.
And so that was the load level. Again, if you're actually looking in 1 second samples, the load level doesn't get that detailed, but you can look at the run queue space itself. We'll come back to that later. But the load levels include I/O waits and other things other than runnable processes.
Right.
Including what looks like to me on MemSQL processes that are handling socket connections too.
Mm-hmm.
Okay, the third chart, my memory usage. Green, we got 2 greens. Oh, yuck. So click on that chart. First of all, before you click, look at CPU utilization at the top. What color is it?
That's green also.
No, the title.
Oh, CPU utilization 10.1.10.53.
What color?
The color of the text itself is blue. Below it, you've got the green.
Correct. Correct. Now go into real memory usage and click in it.
Uh-huh.
What happened?
The color changed, it looks like?
Yep. So that's your active chart.
Ah.
You see?
Uh-huh.
So now click on real memory usage and edit that chart.
Mm-hmm.
No, in the chart, not the title. Go ahead, click in it. It's blue. Now go to edit chart up in the upper left.
Uh-huh.
And let's go to plots. And let's select cached over on the left, and let's get it out of a green.
Sure.
magenta or something.
Sure.
For me, when I'm looking for colors, I tend to like what I was used to in Iris with gross view.
Ah,
So, for example, I like red to be bad things, not good things.
that makes sense.
I like blue to be good things. So typically for me, I like green to be free and unused. I like blue to be good. I like red to be bad. That sort of thinking.
Right.
Okay. We didn't get the color change though. So do it again. You didn't apply, which is what I'm suspecting. I got off track here.
Yeah, hold on.
Plots.
Okay.
And then apply.
There we go.
It doesn't look like, did it change?
What?
I don't think it changed yet. Go back and try again. So you're clicking on cached.
Yeah.
And then plots. Oh, see, when we click the plots, we're losing the selection. That's why. So on plots, now click on cached.
Uh-huh. Oh, I see.
I think we lost. Anyways, go ahead and pick a color. That's good. And it's still losing it. That might be a bug. I don't know what's going on there. Well, anyway, cached is basically the page cache.
Mm-hmm.
Buffman is my rough. You got a call? Go ahead, take care of your phone.
Yeah, hold on. Just will take 1 second.
Yeah, go off phone if you're private.
Hey. Yeah. Sorry about that, Dave. It's all taken care of.
Sure. So anyway, while you were gone, I fired off something.
Oh, wow.
Now look at the time example down on the bottom. We're looking at about a minute,
Mm-hmm.
right? So go under Edit, Samples.
Yep.
And drag both of them all the way to the right. There you go.
Mm-hmm.
Now notice there are holes in the data. We're dropping data. You can see where the data drops are?
Yeah, I do.
Let's see. So I can see some blue that's user time, some red that's system time, and some light blue that was my IOA.
Mm-hmm.
And I can see my load level went up to about 30. This was a 40 CPU system, so my CPUs weren't totally loaded, and the utilization above shows my CPUs were also not completely utilized.
Right.
My memory went to all of other. Other is a PCP number that correlated to the old free.
Okay.
Now, I always hated these engineers that did this stuff because they weren't in the old 2.4 kernels and earlier, they weren't tracking how much memory was being used by programs. They only tracked how cache got and how much memory was left.
Oh.
So there's a lot more detail to memory than is available here. So other was basically anything that wasn't cached in BuffMem.
Mm-hmm.
So they basically took the total and subtracted everything such that anything that was not cached or BuffMem or free, that was counted as other. Nowadays, we have a lot more detail to it.
Mm-hmm.
By the way, I killed off that work that I fired off.
Yeah, I noticed.
I was thinking, and by the way, let's do one more thing here. File, open, view, swap. Let's get swap.
Mm-hmm.
The fun part about this or not is finding the stress that's going to make the number move, make it big, but not tip the system to where you've just stuck it for hours, right?
Yep.
There's a fine cliff, and to be able to boggle your stress right on the edge of that cliff and still be able to look at it without it tanking the system, that's the fun part.
Yeah.
So when I try to write labs, they're written for a particular machine size so that the student can fire up the right workload for that machine. But here I moved something, and I was on Marvin with 12 terabyte, and this one's only got 256 gig, and I was asking for 100 gig processors.
Mm-hmm.
So notice we have swap allocation now.
Mm-hmm.
Looks like about 6 gig that's out on swap now. I'm just curious, go to top.
Yeah.
Okay, go to F. Down arrow to swap. About 2/3 of the way down. 5 more, couple more, there. Space bar. Let's also sort by it. Now, before we do this, look in the upper top line. The last characters are what?
The last characters are...
Of the top line. Sort field is...
CPU.
Okay, now hit S.
Swap.
You're now sorting by swap. Okay? Let's do a Q. And the real thing here now, let's see, where's the swap? The swap field is over on the far right.
Yeah.
Okay, we could move it, but I'm not going to move it right now. But basically what top has done is taken the virtual and subtracted the physical typically. It's not truly what's out on swap. At least it hasn't been in the past.
Yep.
But that's a good target, those JavaScripts that are probably like the Mega Rate Storage Manager stuff and Super Doctor that might be running.
Mm-hmm.
Anyways, let's quit out of there. I was just talking about the fact that we got to swap. Do a swap on -S. So there's our swap device, and we can see that about half of it's used. Now, I don't know how well this will go. Do a swap off -A. Let's go back to PCP now. So there I can see down on the bottom, all the free of swap has gone off.
Yep.
Go down on the bottom and click on free to get it out of the chart. And you can see the red is starting to creep down. Okay?
Uh-huh.
We could zoom, but I'm not going to. And if you notice right above that, we can see the disk activity, the reads, as that 6 gig or whatever it was is being brought in from swap.
Mm-hmm.
And it's really hard to see in the top right. It looks like red. It looks like red system time, but I can't tell from here. And I'm not really interested right now. But in any one of these charts, I can select that legend and take it out of the chart.
Mm-hmm.
However, go to the top utilization chart and click on idle. No, in the chart. Yeah, there. It didn't enlarge anything because we're still on a 100% plot.
Mm-hmm.
Whereas down on the other ones, when I deleted free, that allowed me to see the real stuff. But that doesn't work for CPU utilization. Go ahead and select idle again. Nope. Yeah, there. Where you, yeah, okay. Questions?
None.
Okay, so we're going to take this a step further. Under File.
Yep.
And Open Tab. Add Tab. There we are. Add Tab. Let's call this Memory. And OK. So you see the tab. Click on it.
Yep.
Now this is what I like. I can put up 10 different tabs and be able to pop between CPU, memory, disk, I/O, and be able to get a snapshot and correlate things as I zip through the different tabs.
Mm-hmm.
Go to New Chart. So this is something that I've always done, and the PCP developers accommodated me a little bit about 15 years ago, but they haven't fixed it, and when I asked them to fix it, they would rather remove it. So I said, okay, never mind. So we want to build a memory stack chart that is better description. Keep in mind, most of these tools are still thinking 2-4 kernels, but we have a lot more information in MEMinfo than we used to. So click on the plus sign in front of MEM.
Mm-hmm.
And again, knowing a PM info, printing it out, I know how these metrics are nested and stuff. But click on util.
Mm-hmm.
Yep, there you are. So I'm going to build a stack bar chart. And this is all personal preference on what you put in the chart and stuff. I kind of have at the edge of getting too many, so I don't plot some things that I'd like. But we're going to go from the bottom up. So scroll down to slab. There it is. And left arrow. See the green arrow? There you are. So the slab is the kernel heap, and there's a slab top that can tell you what's in it. For example, on Marvin right now, page tables are huge.
Yep.
inodes and directories would be in the slab. The page cache buffer header chain is in the slab. Network sockets are in the slab, all those sorts of things. There's a proc slab info that will show you the names of the structures that are in the kernel slab, and I like to call it the kernel's heap. It's basically an area where it's dynamically managed. Which, by the way, when you run out of memory, the slab is the first thing that they try to trim. And if transparent huge pages are on, it will try to do a garbage collection on the slab.
Right.
That's called compaction. So people will turn off THP because they may not be aware that the problem is really the compaction. Not that THPs are that much worse than huge pages, but I'm just saying the compaction is the one that gets hit the hardest in terms of performance. So you can turn compaction off and still have THP on. Anyway, any questions on the slab?
No.
Okay, so the next one is, again, I'm doing it on mine. Scroll up to dirty.
There it is.
And left arrow. Oh, I don't like blue. Let's change the color. Go to plots.
Yeah.
Over on the right. Up. There, plots. And let's get it from a blue to a red. I like a red. And then the arrow. I think you lost everything. Huh.
Okay.
Hold on.
Well, it created a chart. Let's cancel. So it created the chart. So
And
now
it's
go
still
under
blue.
edit. Go under edit chart,
Yeah.
and now we're back to where we were.
All right.
Select it. Get the color, and then the arrow. See the green arrow?
Yeah.
Okay, color. Color first. Let's get it to red. Oh, there we are. There. That one worked. Okay?
Okay. Yeah.
And
Okay.
it's just
What were the
personal
other?
preference, but go ahead and hit OK. So there we are again. But now let's go back to edit chart. I could have just kept it as it is, but edit chart and metrics. So now we're going to go under mem again.
Mm-hmm.
And then util,
Yeah.
and we're back to where we were. Now, dirty data is data that the program has written to disk, but it has not gone to disk yet.
It hasn't been flushed.
Correct. This is your default I/O called cached I/O or buffered I/O. When I do a write, I could be in VI and do a :W. That writes it to the page cache, but it's not going to flush to disk. What if we're going to change it right away? So there is a window before it's actually flushed to disk, which by default is basically 30 seconds. So once my data is in memory for 30 seconds, the flush daemon will kick in and start flushing it. And then it goes from dirty to write back. So scroll down and let's add write back to this. If you're seeing amounts of write back, your file system is not keeping up. We did have the problem that MSQL, in writing the persist directory, we were writing it to large hard disks with a lot of head movement, with a lot of directories and a lot of threads, and we had a lot of write back during the flushing of that persistent data from memory to disk. I'd like to get it on NVMe, but we weren't sure there was enough disk space for NVMe, so. Well, I don't. Our colors are kind of screwed up, but let's just leave the color alone for now. Okay. So when I write, like I open a file and then do a write system call. It goes from my application space to the page cache. The flush daemon then says, "Oh, it's been 30 seconds. We got to make it coherent," so it then flushes to disk. By the way, if this is a cluster situation, all the nodes that are part of the cluster will get locked out and they can't touch that file until the write is done, because they have to be coherent to the file. So if my data in what I've written is still in my memory's cache and not out to the SAN yet, none of the other Lustre clients are going to see that same file until the flush occurs. So Lustre makes that coherent and locks the file and makes sure that you get a coherent file.
I see.
So there's communication between the metadata server that controls the file access and the clients that are doing I/O to the file.
Okay. So
this dirty write back has to be made coherent in a cluster situation as well. NFS does not do that, but Lustre, for example, does. Now, I'm going to keep it simple, but the next one would be NFS unstable if I'm writing to NFS, but this is going to be an NFS server, not an NFS client. And I'm just keeping it simple. So if I was writing to an NFS server like home from Marvin, then it would go dirty to write back to NFS unstable. And then it'll go what's called clean.
All right.
So scroll up. Clean _ cache. Down a little bit further.
There it is. Cache clean.
Now, this is one I had them add for me decades ago now. And this goes back to gross view on IRIX again. Now, at the time, you only had used and buff and cache. You didn't have application space and stuff. So what cache clean was basically taking cache and subtracting dirty and write back from it. That's what it was. But now you also have other things that are part of the cache that are counted. For example, shared memory, NFS unstable. There are additional things that should be subtracted out of cache clean. So when I ask the PCP developers to update it to the modern MemInfo, one of the problems is these numbers can go negative because they might be off on their arithmetic a little bit, and they didn't like that. So we just left it alone. They don't want to have to explain my numbers. And by the way, gross view on IRIX did the same thing. It would actually wipe out the display when the numbers wrapped, went super big to a negative.
Mm-hmm.
So cache clean is really not up to date to the latest MemInfo, but politically I can't get it changed. Okay, the next one is going to be BuffMem.
All right.
Let's add BuffMem into the chart. BuffMem is my raw I/O. By raw I/O, I mean I'm going straight into /dev. Oracle ASM disks are raw I/O. File system repairs, MakeFS, XFS repair, those sorts of things are all doing raw I/O. I can do an MD5 sum. I can do a DD on a drive. Those are all raw I/O. There's no file system. There's no inodes. There's no directories. I'm stepping on the raw device.
Mm-hmm.
Also in BuffMem are my journals. I can create an inode storm where half of my memory would become BuffMem, which was all the journals, and the other half was all the inodes. So I built up a large machine where I got half of my memory just all journal activity. So that's the basics for BuffMem. Again, BuffMem is this. By the way, when I run out of memory, BuffMem is the first thing to get thrown away.
Mm-hmm.
Now, I said that the slab is the first thing to get trimmed, but when we go to the slab, the BuffMem is the easiest thing in the slab to throw away. So when you're watching a trim, the BuffMem will go first, but it's really in the slab that the trim is occurring.
Mm-hmm.
Okay? After the slab, then it goes for the caches, active and inactive. Then it goes for the application, and then it swaps. Okay? How are we doing? Any questions right now?
Nope. Everything makes sense.
I'm trying to make that memory a more detailed map than cache, buffered, and other. I'm trying to get more information. I want to know what the kernel is. Remember, dirty and write back is locked up memory. You can't do anything with that memory until it's flushed.
Mm-hmm.
Okay, so the next one, let's go over on the right, and let's do a non-pages there.
All right. I also see a non-huge pages.
Yeah, it could be a non-huge pages as well, but I'm not worried about that right now. So a non-pages is my program space.
Okay.
That's my arrays, my data. By the way, pointing this out, we'll come back to this later, but my executables, my binaries, my libraries, they're in the cache. And when I run out of memory, the cache gets trimmed to 0 and all my executables get thrown away.
Right.
I've been complaining about this for maybe 20 years. IRIX had a floor and a ceiling to the page cache. Linux needs that. They did add a ceiling to the page cache for Novell on the SLES kernel. But that was for SAP. In fact, go to NFS server behind you. Do a sysctl, sysctl-a and grep for limit. Space -a, pipe grep limit -a. No A on the end. I don't want the A, just the limit. There it is on the bottom. Page cache limit for MB.
Yep.
If my page cache gets to 64 terabyte, it's going to take me hours to trim that.
So let me ask you this then, Dave. If
Why would you want to have a floor for a non?
So that I don't throw everything away.
Oh, okay.
Excuse me. I want to leave some memory available for shared text and stuff.
Uh-huh.
So I want both a floor and a ceiling. And that was handy on Iris.
I see.
But the floor is to say trim, but leave me 100 megabyte for DSOs and libraries and shell and stuff at least. That's the thinking.
Mm-hmm.
Okay, so let's go back to PM chart.
Mm-hmm. Oh, sorry. Hold on.
You're, yeah, there you go. So that's a non-pages. That was my process space. There are a lot of other things in there, but I'm not caring about them right now. So the last one is free.
Yep.
Now let's make that green.
Okay.
Make it bright green. Click on it again. See the bar on the right, far right? Just drag that up to the top. There we go.
There we go.
Yeah, that looks good. Now, before we go, click on chart now
Yep.
and make it a stack bar. I don't care about title. You can get fancy and stuff, but let's click OK. So we had about a 256 gig memory system, and I can pretty much see all of my memory there over on the left.
Yep.
Now, it is possible for something to be missing or double counted. So it's possible for this type of plot to not match the 256 for a while, but don't worry about that.
Okay.
So there are other things in there, mapped, shemem. There are other things that might get double counted or even triple counted, and other things that might be missing. So it's possible to actually say, well, I can't account for my full 256. Something's taken it, but I can't account for it. Huge pages, for example, things like that. So, you know, it's like take everything with a grain of salt.
Mm-hmm.
You got to be able to look at the data and say, well, I don't believe what I'm seeing. Let me go check to see the real numbers, or this looks like garbage. That number is too big to be realistic. You know, those sorts of things. You don't believe everything you read. This is the National Enquirer.
Right.
Okay, click on free. So I can see my non-pages are at about 6 gig.
Mm-hmm.
Hang on. Uh-oh.
Did you just kill a bunch of programs, Dave?
Yep.
Looks like they're back.
I just killed them again.
Uh-huh.
So that was memhog.
Okay.
Well, let me just do one. Memhog. I'm going to go 100 gig. Unfortunately, our brown kind of looks yucky. But anyway, I'm more used to a blue. You know, everyone has their preferences for colors and stuff. I don't really care.
Sure.
Okay. So
This all looks good.
hang on here. Let's see if this is going to make... So the point now is to try to make the numbers move and do something.
Mm-hmm.
So what's happening now?
So I'm seeing buff mem is climbing too. Seems
Sure.
to be at the same rate as the non-pages.
Yeah, but the non-pages are writing on top.
Yeah.
Click on Buffman. Click on Buffman. Take it out.
Yeah.
So Anon's not really growing. Okay?
Uh-huh.
It's just that it's riding on top of a metric that's growing.
Oh, I see.
It's a stack bar. It's a
Right.
stack bar. That's the advantage of being able to click on these different ones and look at them more closely. Let's go look at the slab. Deselect everything but the slab. And
Wow.
you can see the slab is growing now.
Yep.
Now you got to have perspective. We're going from 100 meg to 200 meg right now.
Mm-hmm.
Okay? So how can I figure out what that is? Let's go to your window behind you.
Yep.
And let's do a slab top space dash S space C dash S. And then we're sorting by the size, the memory footprint. Go ahead. Oh, I'm surprised the task structure is that big. I was expecting to see buffer underscore head growing in here. I don't see it really growing. Radix tree node is growing. That's part of the buff mem. And you got to be careful. Kernels are always changing.
Mm-hmm.
So the developers always hated me running these classes because every kernel might have something different.
Mm-hmm.
I am surprised that the task table is that big. The second task underscore struct, right?
Yep.
See that?
Mm-hmm.
PS prints that. That's the process table. That's what the PS command goes into.
Okay.
So I had a problem on Marvin a week ago. They had 120,000 processes of memSQL.
Mm-hmm.
And the process table became the bottleneck.
Okay.
Anyway, let's quit out of there. Bring up top again. So that looks like it might be my application, MD5 sum.
Uh-huh.
But again, we can't tell. That's just top of the percent CPU. Quit out of there. Let's do an IO top. IO top. Let's do a zipper install IO top. Yes. And now try your IO top. And there, MD5 sum is at the top of the list. I also get an argument there, SDN. Let's go back to PCP for a second.
Mm-hmm.
Let's go on to the live. Look at live.
All right.
Go to the live tab. And you can see where the disk write started as well. Or reads, I mean.
Mm-hmm.
See the reads? And notice I'm
Yeah.
correlating. So I see the yellow reads, and I can see the buff mem growing at the same time.
Yep.
So you see how nice it is? Flip back to the memory one.
Uh-huh. I do. Let's see.
You're going up to the memory tab and flip there. Okay, so you can, add them all back in again, buff mem, that sort of thing. Now, one thing we didn't have, let's open up another tab.
Mm-hmm.
Add tab. Let's call it disk. And then click on disk. You're pretty much there. So I want a new chart, not open view, new chart. Close that one. We already have disk on the other one, but now click on disk. We're going to go for more detail.
Yeah.
And I want by device.
Uh-huh.
Now, when you get to the FIO experiment, you'll probably want to do it by device or device mapper. I don't care which. So let's look at expand the block read. And then what device was this again? N.
Okay.
Let's select N. Left arrow. That's good enough. Okay. Notice NVMe are in there. Now, I've refined this for the file systems on FCL server. And you grabbed one for that, but I haven't refined it for this one. Okay, let me fire this up again. SDN. Well, I should be reading some disk activity by now. Huh. I'm not going to completely believe that PCP is giving me good numbers right now. Go back to the terminal behind you. Oh, what's going on? MD5 sum's not even, I'm running it. It's not in top right now. Break out of there, bring top disk up. Type in top disk. Now that came from SGI. So it's, yeah, I don't have any I/O going on here. Why? What's going on? Well, let me try something else. Let's go back to PCP. So I'm able, this is strange. I don't know why I'm seeing a count per second when it's blocks. Must be blocks per second. I'm not liking the label on the left. The label on the left starts making me think in terms of IOPS or something. Let's close that chart. And by the way, I can't see the I/O now. Move that out of the way so we can see the device behind you. There we are. So let's use DM1 this time. We used SDN last time, but that didn't seem to, at least for blocks, I didn't like that metric. So file, new chart.
Yeah.
Disk, device. No, let's go to DM, sorry. We were going to go to DM this time. And then let's use bytes this time.
Okay.
Read byte. And we only want root right now, root B, that's good. Again, when you get to your other experiment, you'll be picking out other things to look at if you want. And now let's add into there write byte. So new chart. No, there. New chart. Disk. DM.
Up there it is.
And we're going to get the right bytes and apply. And let's see. We got them in two separate charts. Just cancel.
Oh, I
could have kept them. I was going to originally keep them in one chart, but that's okay. I'm just getting you used to this, right?
Yep.
So I can see I'm getting about 200 megabytes per second out of that root disk, which is an SSD. Okay. And let's go back to memory.
Yep.
And notice I got red. Okay, so let's and most of my memory is consumed now. Let's get rid of the top. Let's just drill down now. Get rid of green. Get rid of brown. You can see where the buff mem was trimmed there. Go ahead and get rid of that. Get rid of the cache clean. So you can see the dirty, we got about 30 gig of dirty data. Get rid of that and get rid of the slab. And I'm looking for, oh, we still want write back in there. Sorry. We still want the write back in there. There we are. So that's the amount of data that is flushing. That's the amount of data that's been marked to do a flush. We only got about 150 meg, which isn't bad. Okay? So a write goes from dirty to write back to NFS unstable and then goes to clean.
Yep.
Okay. Deselect all of them. Okay, now I've killed my DB that was doing this, but the IO is going on still. Okay, so that IO is not going to finish until that red is gone. And a sync command would do it. By the way, you can see the red going to green, so you can see where that data dropped, that one line going through. There's a data drop there. You can see where things started moving from dirty to clean as it flushed. So we go from dirty to write back to clean. And it looks like because I killed BD, we basically topped off on the amount of memory that I was writing. Let's see, ls-h. I wrote a 62 gig file. Hey, that's about the memory footprint for it.
Yep.
Now I'm going to remove it. But what's wrong? My RM is sitting here.
Yeah.
My RM is sitting there. My RM just came back. I can't remove the file until the coherency is dealt with. Okay? So that dirty data had to be dealt with. And then once I removed the file in the cache as well, it all got removed from the cache.
Right. Oh, I see.
So the asset in the cache got cleaned up. We're going to come back to that later. But so I got an application on a 12 terabyte machine. It reads in a 6 terabyte file, and all that data is sitting in page cache as well as in the application. And now I got to clean up after myself and trim all that page cache so I can get memory for my application. And that's a real problem.
Okay.
Especially trimming 6 terabyte of page cache. That takes time.
Yep.
So this is a small machine. You know, we're at 256 meg, but when you're talking, 64 terabytes is the whole different beast. Now I've just run a drop caches.
Okay. Wait, drop caches?
Yep. sysctl, I just did a sysctl-w vm.drop_caches equals 3.
And sure enough, I see stuff dropping on the right here.
Now, if I've got huge pages, if I've got shemem, it's not going to go away. Trying another one here. Anything happening yet? Take a look at your other views. You got live, you got disk.
Okay. Some CPU utilization, not a whole lot. I'm seeing more.
You can see a little bit of blue in CPU utilization, and right now a little bit of red, but yeah. Again, our swap allocation is done. By the way, go back on the left, break out of top disk, and do a swap on -A now that our swap is cleaned up. And do a swap on -S. Okay, so that got cleaned up. It takes a long time to trim that stuff. But, if it's quiet overnight and there's stuff out there, I might try to clean it up and pull it back into memory. Any questions right now?
Nope.
let's go back to PM chart.
Yep.
Go under, well, let's just go to record. Go ahead and hit, let's see if we can, let's not. Hang on. You can try it. Go ahead, try it. Record. So it's going to save on your laptop, and I'm not sure it will have permissions to do that, but go ahead and just try OK. And I see the red record button down in the, like I say, it doesn't have.
Yeah, permission.
Yeah, I'd say it's a permission problem to that path. That's typically for me. So I don't really care right now, but if I was on the UV, I could save them or pick a path that I can write into.
Mm-hmm.
Okay?
Yep.
Now also, let's go under File.
Mm-hmm.
Save View. Save View. Yep. Notice where it's saving it.
Yep.
And let's just call this one Basic. And save it. And let's go find that file.
All
It's
right.
text.
All right, hold on. There it is.
Does it make sense?
Yep.
I just sent you email.
Uh-huh. Uh-huh.
So put that into that directory.
Sure. Okay.
And hang on, let me get... I've given you a pre-built view. What's on your mind?
Oh, so. All right, where am I what am I saving this file as?
In your Windows directory by user, there was at the top users directory.
Yeah.
I mean, we saw it in PCP when we did the save.
Yeah.
Yeah. Yep, in that directory, next to basic. Yep, save it there.
Okay.
And let's call it NFS-server. And now that was hard-coded. It has the IP address in it, the .53.
Mm-hmm.
Oh, there, stop right there too. So some of these metrics, there's an instance, and then you can specify a particular instance. Scroll up.
Mm-hmm.
And actually, we'll have to trim it. But right there is an example where under instance, I can see different file systems. Okay? But this has not been tuned for NFS server. I just cloned this off of FCL-DAF server. So I'm not saying, or even Marvin, I'm not saying that this matches our current system. Okay?
All right.
So you can take a look at tweaking one of these to NFS server if you want. All up to you right now. But let's close out of there.
All right.
And close all that stuff. Close PM chart.
Okay.
And let's bring up PM chart again. File, open view. Get your host first. So click on the PC in the lower right, there, 10.1.10.53. Even though it's hard-coded in the scene file, it still is going to default to your workstation. Now, you see the two heads in the upper right. Those two people, click there. There's your views.
Ah.
So when you did the save before, they got saved. There's your path on Windows. John Perlito, .pcp PM chart in that directory, right?
Yep.
So now you can do it open. I'm expecting this to blow up on things, but that's okay. So I have a pre-built one for FCL server and Marvin right now, but I didn't do anything. I basically cloned the FCL server one for NFS server and changed the IP address. Taking a little bit, almost there. So these are all the things that didn't match.
I see.
Okay. And I just click to see if you can close that thing off, that X in the upper right, and cancel. So like number of CPUs and file systems, those are the two big things, the number of CPUs and the file system naming. Okay, yeah, there you go. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tabs. Okay?
Yep.
So let's click on summary. Now you're going to be playing with NFS server until mid-July or so, so being able to tweak and look at this. Go under edit, and let's change the number of samples. These are too coarse. The bars are too wide. You see what I mean?
Yeah.
So grab the slide bars all the way to the right. You can actually start up PM chart to even have a bigger window, but this is 5 minutes now. So the thing about some of these performance tools is they're speedometers. They're instantaneous, what it sees then. If I look away, I've missed things. This gives me 5 minutes of history. Now I can start seeing correlations, effects that are related to each other. Okay? So we got CPU utilization, we got memory, you did that, we got the disk. I've added networks here, and there's a file system full one, but again, the file system DMs have changed names. So that's null. Click on CPU.
Yep.
So now I'm drilling into a little bit more closely, the top one being just my load level. The second one being the number of processes running, runnable, or sleeping on I/O, blocked. And notice those are in the 2 or 3 versus our load level that's still up. Well, I guess it's not that big anyway. Load average is pretty small. Sorry, I'm getting a tickler here. NProcs, that's the size of the process table. If I did a PS-E, that would be the number, plus or minus the PS command itself. Okay, so that's the size of the process table. The next one, P switches, are your context switches.
All right. Yep.
Do you remember what a context switch is?
Yeah, context switches. I have some process going, but all of a sudden the scheduler says, you're done. I'm taking you out. I'm going to start looking at this other process instead. Yep,
that's good. Disconnect the process from the CPU, save its state or context, which are the internal registers, basically, the program counter. But when the context or state is saved, that does not include caches or functional units. Just the program counter and internal registers they're used to jump return and stuff. So it's a CPU swap.
Yeah.
And then the last one I got is just system time on a per CPU basis. And again, the view that we had more CPU, 64, but this system only has 40. So that could get cleaned up. And I'll probably be cleaning up my own as well. Let's click on memory.
Okay.
So that one view I gave you is a multi-tab view. So there I can see most of my cache most of my memory is cache clean,
Mm-hmm.
and my swap is free. So what do we got there? About 140 gig in my cache clean.
Mm-hmm.
A little bit of free, a little bit of a non-pages. So I'm going to drop cache here again. And let's see what we get back. Okay, the trim is done. I didn't get anything back.
Nope.
Click on the blue and the red. Get rid of the non-pages and free.
Okay, a non.
And free.
Yeah.
See, I'll drop cache again. Nothing. I didn't get anything back.
Mm-hmm.
Okay, file, new chart. Memory, mem, util,
Mm-hmm.
shmem, S-H-M-E-M.
Yep. Shemem.
There it is. And okay. So I'm going to be constantly doing this to you.
Yep.
But cache field has a whole bunch of things in it. And notice we got 120 gig that's in my shmem.
Mm-hmm.
Go to your terminal, xterm.
Yeah.
Do an ls-lh on dev shmem. No, SHM, no EM. There you go. And there it is, big file, 126 gig.
Mm-hmm.
There is no limit to how much shmem. Shmem can take all the memory and even swap.
Wow.
Do a sysctl, and I disagree with this, but do a sysctl-a and grep for SHM. Pipe grep.
Yeah.
And see those shem all and shem max?
Mm-hmm.
Those are essentially so big that you have no limit on them.
Mm-hmm.
Okay. Now let's grep shmem, grep SHM, and proc mounts. Let's see if there's a limit on the mount. No, just SHM space /proc/mounts. Yep. And I don't see any additional arguments to it, but it is possible to have arguments to limit. Do a man on tempfs. I guess we don't have man on mount. And then 8. Yep. And then try /SHM.
Nothing.
Page down, just page down. Maybe it's uppercase. /tempfs. Yeah. I was looking for the options on the man page. There are limits, there's memory policy and stuff like that. But let's leave that alone and just get out of this for now.
Mm-hmm.
I was looking for the additional arguments for that tempfs mount point, but I don't want to chew time on that. Okay, let's go back to, before we do that, go back to your PCP chart.
Mm-hmm.
And I'm going to remove that file.
All right. Close file.
So just keep in mind the cached field contains a lot of stuff. Shared memory, shemem, all kinds of different things. So I got rid of the file and now half my memory's back. That can actually be a memory leak. I could have somebody put a file there and a month later all my memory is still consumed by that file.
Yep.
Okay, so just going through the numbers again, we had our swap with free and used. I personally like used to come from the bottom towards the top, but the way they do it is it digs in from the top. I kind of like to see memory fill up and then slop over into the bottom of the swap rather than chewing down from the top. The second one then, we had our kernel slab, and slab top told us about that. Our dirty for our writes, our write back when the flush is kicked in. NFS unstable if it's flushing to an NFS server. Buffmem was our raw I.O. I was just doing an MD5 sum on /dev SDH or SDN or whatever. I was just doing an MD5 sum, getting a checksum for a raw device. That's how I was making it move. And again, when I trim, Buffmem will be the one you see go away first. And then I was talking about cache clean that has a whole bunch of different things in it. Cached has everything in it, and I've taken out write back and dirty to get cache clean. But it should also be taking out NFS unstable and shemem, because those are not cache clean.
Right.
NFS unstable and shemem were not available in procmem info when PCP added cache clean for me. So I got to live with it. Any questions on this chart?
Nothing so far.
So let's click on the next one, node info.
Yeah.
We are wrapping up here. So the top one I'm looking at on a per node basis. I only got 2 nodes here. So I've got free, I've got a non-pages, and I got the page cache. In fact, I can see that shemem big file was actually just on one node. It was a first touch allocation rather than round robin between the nodes. So if someone else had tried to get memory on that node, they would be fighting with me, and somebody's going to end up swapping. So I was just more important on 16 nodes and stuff, but just trying to see on a per node basis. I would prefer to see the stuff in a scrolling heat map, because it's impossible to look at it when it's big. Let's click on the next tab, NUMA. So this, and I see down on the bottom I had foreign, meaning that references for memory were coming to my node. So the top one I see the hits, but the bottom one I'm seeing somebody came into my node because they ran out of memory on their node. That's because of the shemem file. That was the shemem file that we had.
Wait. Actually, hold on. I do have one question here. So I'm a bit confused because we're looking at this is not the UV, correct?
Correct. This is the Supermicro with 2 sockets.
So what's the deal with NUMA then? There's no NUMA link.
No, this is a NUMA machine. You don't need NUMA link for NUMA.
Okay. Oh,
okay.
I see.
NUMA means non-uniform memory, and every socket has its own memory. That makes it NUMA.
Okay.
It's just when NUMA link was created, there weren't really, it was still a front side bus, and we didn't have, and the memory wasn't attached to the socket at the time.
I see.
So it's just a collision of terminology.
Oh, okay. Never mind then.
So NUMA just means a non-uniform memory architecture rather than the central memory concept that was bus-based, back in the day with S-buses and stuff like that. And then NUMA link was simply a way of connecting all these sockets. But original NUMA link, the memory wasn't on the socket. That came along later once they got rid of front side buses and went to a quick path interconnect. And that's when the memory got moved from a central memory concept to a attached to the socket memory. Anyway, so 2 different terms of NUMA. And in fact, Hewlett-Packard was big on NUMA before SGI was. SGI was using Hewlett-Packard machines for their first Linux boxes and stuff.
Oh.
So, Hewlett Packard was into Linux before SGI was, and a lot of the NUMA code came from Hewlett Packard.
Wow.
Okay? So anyway, we'll come back to this, but it says my allocation was on my node, which is good. That tells me there's affinity. But again, I might allocate it on my node like a CALIC, a C-ALIC, and that's not NUMA aware, so it allocates all the memory on one node, and then I fire off a thread that's on a different socket, and now it's coming to my node to get the data. So there's a difference between the allocation being on socket or on node, and then the later references to that address. We want them both to be on node. That's where you get so that's why you get into pinning and stuff. Okay? So foreign simply says something came off, somebody started allocating on my node, they're foreign to me.
Mm-hmm.
And I could be plotting the ones that went off node, but I'm just plotting to keep it simple. Let's click on the one. Paging. So these are coming out of the proc vmstat file. And I'm just interested in them. They're not highly concerning right now. But the top one is meaning that I tried to allocate memory, but there was a stall.
Mm-hmm.
I don't see that very often, but I keep it in there so that if something happens, when I'm looking at the last 5 minutes, I can see if an event happened. Okay? The second one, inode steals and K-swap steals. This is where K-swap's trying to trim. So that says a socket, and this is on a per socket or per node basis. Each node has its own K-swap. So we have 2 K-swaps on this machine because we got 2 sockets. We got 16 sockets on Marvin. Each socket is managed on its own. If one of those sockets runs out of memory, then K-swap D is going to try to figure out, okay, what pages can I steal and get rid of to clear memory for me? Unfortunately, it'll often go off node before it finds something to steal. And that's why I like to trim with drop caches. So next one are my page allocations themselves. Each socket, only one allocation can occur on a socket at a time. So if I have 4 processes growing on the same memory node, only one of them can grab the lock and you'll have system time for that allocation. So basically, each node or each socket has a lock on its memory when memory's growing. Only one process can grow on a socket at a time. Okay? And then I'm looking at deallocations or frees. And the last thing is swapping. Are there any pages? Actually, swap page in, swap page out. I don't care so much about the swap outs as the swap ins. Swap outs can go on in the background. But swap ins means I've got a process waiting for it. Okay, I'm going to skip over huge pages. Let's go to I/O. Again, when I'm looking at a workload, the first thing is I'd like to be able to see the big picture of all this before I'm looking at 1-second samples. I don't know how these numbers fit into the last month. Okay? So the top one here is how much is in memory. So this is part of my slab. How many directories are cached in memory? How many files are cached, or how many file descriptors, how many open files are there, and how many inodes are in memory. So the directory counts and inode counts are not what's out on the file system, that's DF. These are just what's in the slab. Then I'm tracking number of read and write I/O operations. So an I/O operation is simply a packet that says position your head here and transfer this number of blocks. And there are other IOPs to do rewinds and stuff like that. And then the third one there, the number of bytes read and written. Problem is now, that disk all, multiple counts things. So it's adding everything. Go back to your X term, your putty.
Yep.
Do a *-DP, SAR-DP. Yep, that's good. Hit enter. Oh, we don't have SAR turned on yet. Let's do a system CTL grep for systat. Oops, CTL.
Oh, CTL, sorry.
Systat, yep. It's not even loaded. Zipper install systat. Oh, wait a second. SAR is. There must be another. Yeah, do an RPM QL on systat and pipe it in more. Yeah, good. I'm looking for the startup script. And I'm not even, there we are, RC systat. But that's not the one I was really, oh, there it is, systat.service. See it? Lib
Yep.
system D system systat.service. So let's quit out of there and do your system CTL enable systat.service and then start it. Now we'll come back to all these tools again. I just wanted to give you some tools to look at when you're looking at your workload stuff. Now we don't have any data yet, so just do a SAR-DP space 1 space 5. That's good. So notice it's got devices more than once.
Mm-hmm.
So SDN is also root B. So back on the other chart now, basically SAR that go back to PM chart now.
Mm-hmm.
That last one there is basically adding up everything that we just saw in SAR-D, and things are double counted when there's MDs and DMs and stuff like that, even triple counted.
Mm-hmm.
So you can't read that as the true bandwidth that you're getting, because you will see multiple counts there.
Mm-hmm.
Okay, let's click on the next one, LVM.
Yep.
Overnight, I'll give you a cleaner one. So none of our LVMs matched anymore. Let's do go under File and close Charts a few times. Close Chart. There. And just try to get these empty ones out of there.
Close this one too?
Yeah.
Okay.
So now File, Open Chart, or New Chart, I mean. File, New Chart. And we want to go to Disk DM. Let's go to Disk DM. And let's just pick total bytes, just for the fun of it. Total bytes there.
Mm-hmm.
And then select root B, put it to the left, and then OK. Okay. So I just fired something.
I see it.
Let's click back to summary.
Mm-hmm.
And make it full. When we drop the charts, it kind of freaked it out a little bit. Okay, so you can see a little bit of system time up on the right, but it's not very clear. You can see cache growing there on the second chart. You can see the right. Again, we're getting about 160, but again, that is probably double counting. We have to be careful of that.
Mm-hmm.
And I don't care about network. Let's look at CPU. So there we can see the IO8 with that blocked, the red there. And I can also see the system time. And by the way, I can see my DD that I'm running here is flopping between CPUs, because I can see it going to, by the way, on that bottom one, the CPU sys, one is 100%.
Mm-hmm.
So we're close to 100% CPU time. But it's flopping between different CPUs. It's one thread, and you see it bouncing around. And again, it'd be nice to have that in a heat map instead.
Yep.
Any questions? Let's go to the third one, memory.
Uh-huh.
So there we can see the red went dirty. I'm not going to zoom into the right back, but you can see how the red is going yellow.
Mm-hmm.
And again, blue's not growing, it's just riding on top of the cache that's growing. But you can see that this red is turning yellow, and that's the file. I've got one file being written.
Mm-hmm.
Okay, let's look at NUMA. I'm not expecting much there. Not sure why we have some foreigns. Let's look at the next, or no, prior one, node info. File pages, 35 gig, 120. I'm not sure why I'm seeing the second one and non-pages. There still looks to be free memory. I'm not sure why we're going off memory yet. There's still about 40 gig available in Node 0. But anyway, let's look at paging.
Yep. Let's see, paging.
So you can see the allocation, mostly for the page cache. That's page cache being shown there. Let's click on I/O.
Yep.
So there you can see the reads and the writes and the write bytes.
Mm-hmm.
And let's click on LVM. So that LVM looks like it is getting about 190 megabyte per second, which is pretty good. It is an SSD.
Mm-hmm.
Any questions?
Nope.
Let's look at the last tab, XFS. So this is really digging deep now. So the top is basically, the B tree is the hash algorithm used for blocks and directories and stuff. So these are hash trees that we have allocations and compares and inserts and stuff like that. Again, there's a lot of metrics here. I only care about them if they correlate to an event that I'm digging into. Second one is where I'm actually allocating blocks or allocating extent. An extent is a contiguous piece of the file. We want minimum extents. If we got a lot of extents, we're fragmented.
Right.
And then I'm just, again, looking for these so that I can look for correlations if some sort of event is occurring. But basically, my page cache, do I have anything busy, locked? I'm allocating buffers for page cache. I'm getting them, things of that sort. And we got some sort of, what is that, about a 30-second between those ticks, 1536 to, it looks like about 30 seconds between those when something's waking up.
Yep.
Okay, the last one then is actually directories being created, looked up directories and directories being deleted.
Yeah, not a whole lot there.
3 doesn't, well, we have a burst there, but they're still in the 7 range, so there's no metadata storm going on right now. Okay, Extended 3 and other OSs don't have a whole lot. That's why I was interested in that journal activity that we saw when we were in PM Info. Anyway, let's go back to Xterm. We are wrapping up here.
Yep.
So, do a top.
Oh, top, sorry.
There's my DD.
Mm-hmm.
Sadly, top does not separate user time and system time.
Yeah.
That's just total. That's just total time. But notice the S field is a D.
Mm-hmm.
That D says it's non-interruptible. Okay, so 32112. Quit out of there.
Yep.
CD into /proc/32112. Cat stack. Cat space stack. And there we have a write. That's strange. So we're starting off with a system read, but then there's a VFS write. I don't recognize some of these routines. The per CPU up read, IO vector iteration 0, but then we got a XFS write going on. I'm not sure why the system call started as a read and ended up as a write, but oh well. So you read a stack from the bottom up. Okay, let's do a watch cat stack. Boop. You need a space. And there we're flushing inodes.
Mm-hmm. Yep.
Now, this stack that we're looking at is a sleep stack.
Mm-hmm.
So this process is in a WB_wait for completion, sleeping.
Mm-hmm.
So this stack file is always showing what's sleeping. Let's quit out of there.
Yep.
Bring up top again. Type in F. And then down arrow to WChan.
Yep.
About 5 more. There it is, space bar. And then Q to quit. And you got to slide the window over.
There it is.
The command name is a big column. And I'm looking for DD. Let's see. I'm not seeing DD in there for some reason yet. It must be sleeping still. Let's see. I was waiting for the DD to show up. XFS activity. What are we sorting by? Let's see, I don't know how we can catch this. Let's quit out of there.
Mm-hmm.
Do a PS-EL and pipe for DD. Yep.
3, 2, 1, 1.
I'm looking for WB wait. But because this process is never running, it's in a D state, it wasn't showing up in top.
Yep.
Okay? But you see the WB_wait?
Yeah.
So that's what is cat stack.
Uh-huh. Cat.
Process died. Do a DF.
Oh.
Do a DF. 100% full root.
Yep.
I'm removing the file that I was generating. That might have been why DD had fallen down on the top list, because it was what we were seeing. It was just scraping away at the last minute there.
Mm-hmm.
Okay, so the process is gone. I just started another DD. Find out what his PID is. PS-E, grep for DD. And notice it's R running because we have not started flushing yet. PD into /proc.
Yep.
/32212. 32212. Watch cat stack. So at least this one is showing a write. And seeing a buffered IO, inode unlock, there's a write iteration, write begin, all that kind of stuff. Balance dirty pages. Just trying to spread them around or something. Again, these subroutines can change, and you kind of recognize what general functional area it is. You can tell it's memory or CPU or I/O or network or something. And then if you're really interested, then you go into source code. Look, I'm waiting. Let's take a look at PCP there.
Yep.
And let's go back to I/O. Let's just look at the I/O one. So there we can see the writes, disk writes. We really don't know if it's actually going to disk yet. Click on summary. And there I can see. So I was seeing, you see that magenta in the middle there or whatever?
Yeah.
Right at about 1525. You can see actually the cache growing there above it, the system time above it. But you can actually see on the top chart when it went out of system time and fell into a sleep mode. It's hard to see, but can you see where the red ends and it turns solid cyan?
Yeah, I see it up top.
It's kind of hard to see, particularly if you had more CPUs. You could have one CPU that's busy and bottlenecked on I/O, but it's lost. And that's why in my second chart I was looking at it on a per CPU basis. Okay, wrapping up here. Go back to Xterm, buddy.
Yep.
Break out of there. So, get the perf record -G -P through 2212. That's good enough. Just hit enter. Oh, zipper install perf. No, I'm going to look at this DD with perf, and then I'm going to look at it with strace, and then we're done.
Yep.
If we get past this.
Yep.
Why? I'm actually going to kill that process in the end. So it's going to change again. I just didn't want to fill up root. But it does really annoy me. The SAR developer puts metrics for memory that are pretty useless and isn't paying attention to the ones that matter. Because they weren't available 5 years ago with 2.4 kernels. And we're still bottlenecked on the I/O. What do we got there? About 18 gig that's still in memory trying to be flushed. Okay.
Let's try this again.
So I'm going to start a different DD again.
Oh, okay.
So the PID is going to change. I didn't want to fill up roots is all. So, okay, I've started a new DD. Go ahead.
Try that again.
Why is it not showing it?
There it is.
Wonder why it missed before. Must have taken a little bit to actually get the process table. Huh. No, you don't need a PID. I don't think it did anything with that.
All right, let's try this.
Yep. And again, some people might put a sleep after it. Oh, we can't do it in that directory. You don't have write permission. CD into temp or root or something. And I'm being lazy and just using perf.data for a default output file. And I'm being lazy, not putting a sleep there and saying, well, I feel comfortable, you know, how long do I have to wait? Now, if I was on Marvin, perf is unusable. It spends all of its time reading page tables.
Oh, wow.
Good enough.
Okay.
Control C it. So we did get 675 samples. Not a whole lot, actually, if you ask me. But let's do a perf report. And there I can see the top glibc, an entry system call. I can see it was all writes. Do a -E to expand.
-E?
No, just a capital E.
Oh.
There you go. So with the -G, I can actually see the entire call sequence. This is the user time, not the sleep that we were seeing in stack. This is the user run stack, not the sleep stack. Okay? And if you scroll down, I can see where pages were being allocated for the write. Scroll on down if you can. You can dump these into a text file too, but I'm trying to get to the bottom where it all starts. Still looking for really the start. There's an AIO write. There's the journaling activity, the Xlog grant stuff as it's writing. And I don't know, I'm good enough now. Let's quit out of there. Okay, so now let's do an strace. And stash 2 little t's and a big T.
All right.
Space, -P. And then your PID, 32614. And Control C. You can break out. Now, strace will impact your application. It will slow things down. In fact, I've had many a case where attaching it with strace slowed it down and the problem went away because the intensity of the process I attached to went down. Does that make sense?
Yeah.
So strace can impact things because it is heavy and it will throttle back the intensity and then your problem could go away. So I see reads and writes. Then I've got a 0 or a 1. That's your file descriptor.
Yep.
So when I open up a file, in this case, I'm opening up dev0, and then I'm writing the file descriptor 1. So this is, you know, standard in, standard out, less than, greater than signs. Okay? So the 0 or the 1 is the file descriptor, which is basically the offset into the open file table. Okay? Second argument there between the quotes is the data, and I'm writing dev0. Third argument there is the number of bytes that I asked for on the system call. After the equal sign is the status of the call. So different calls will have different meanings to what's after the equal sign. So it could be an error status, for example.
Right.
In this case, it's the number of bytes that actually got transferred. So if I hit an into file, if I said move 10 K, and I only had 10 bytes and hit an into file, the after the equal sign would be the actual bytes transferred until it got to the into file. Okay. And then your T's added the timestamp on the left, and in the brackets on the far right, that's the wall clock time of that system call. Not the system time. It's the wall clock time. How long did that system call take to complete?
Right.
So we are doing 5 12-byte transfers here. Not very efficient. Okay?
Okay.
Now I'm going to wrap up for the day,
Okay.
but this gives you something to think about, because rather than just running the FIO script, it would be nice to poke into it now and then.
I agree.
Okay, so you can do your explorations and stuff. And again, this I/O I was doing was through page cache, but FIO, we're doing it direct because we're measuring the disk, not the cache. Any questions?
None right now.
Well, that's a pile full for you for the day.
Well,
a lot of
good.
it should start to be review on the memory and stuff, but we're just going to come and keep digging back into this.
Agreed.
But I've got you started on Performance Copilot now.
Yep.
And at some point, I need to get Tianwen and others in College Park to use Performance Copilot a little bit more to see, well, it's not swapping, and give me a little bit more instead of me watching for them. I don't mind watching, but I would like others to understand what it's telling us. Okay, stop the recording, send me the link to it, and let me know when you have